We're now going to have a look at adiabatic processes. So I mentioned this funny word earlier, adiabatic, or adiabatic, depending on how you want to pronounce it. And what does this mean? Well, we introduced it alongside the three different gas laws, isothermal, isobaric, and isochoric. But I also introduced this other type of process, the adiabatic. And so, what does this mean? Well, adiabatic simply means that there is no heat in and no heat out. In other words, Q equals 0. There is no heat entering or leaving the system. And so if we go to the first law of thermodynamics, which stated that the change in internal energy is equal to the heat plus the work, then if Q is 0, then you simply get that delta U equals W. And so the only way to change the internal energy is to do work on the gas. And that is basically what an adiabatic process is. It's no heat in and no heat out. So what is kept constant during an adiabatic process? Well, actually nothing is kept constant apart from this thing called entropy. Now, before I go a little bit further, I'm doing a series of videos about thermodynamics and I haven't mentioned anything about entropy, so it's probably about time I do. Now, entropy is a sort of a weird thing, really. It's much harder to visualize than temperature, pressure, and volume. But essentially, it's a measure of the disorder. And when we come on to statistical physics, then we'll see that entropy is a measure of sort of how disordered a certain state is, or how disordered a certain microstate is. But for now, we're going to go with the thermodynamic definition of entropy. And what it is basically the heat divided by the temperature. There's kind of like a loose definition of entropy. It's the heat divided by the temperature, and we normally give the symbol S. So you're probably thinking, well, what's the difference between entropy and heat capacity? They're both heat divided by temperature. Well, heat capacity is what I said was delta Q divided by delta T. But entropy is a little bit more subtle than that. It's a state variable rather than a process variable. Of course, heat capacity was a process variable, but entropy is a state variable. And changes in entropy often happen at constant temperature. So there's no change in the temperature. An entropy change sort of happens at constant temperature, but not in the same way as an isothermal change. It's a slightly weird concept, but basically changes in entropy don't happen when the temperature is changing. And a more mathematical definition for entropy, S, is this. So what it really is, we don't really talk about what the entropy is itself. We more talk about the change in entropy. In fact, really, what I should do is sort of say that the change in entropy, delta S, here is delta Q divided by T. With heat capacity, it was delta Q divided by delta T. You just simply use, if the temperature is a function of other things like volume or pressure, then you simply substitute that in. But delta S is essentially delta Q divided by T. But a more slightly useful definition of entropy is this, and it's ds is equal to dq divided by T. Now, there's another term which I should really have introduced by now, to be honest, and it's called quasistatic. And what the hell does quasistatic mean? Well, a quasistatic process is not like a sort of, isothermal, adiabatic. It's not a type of process in that sense, but it's basically a sort of condition which we like to use a lot in thermodynamics in order to make the maths work. When a process is said to be quasistatic, then what that means is that it's always in equilibrium with its surroundings. And so generally what that means is that the process is done so slowly such that the system is always in thermal equilibrium. So what do I mean by that? Well, let's draw out a box right here. And this box is maybe increasing its volume, or there's heat coming into this box. Let's say it's in a heat bath. We like to use the concept of a heat bath. So it's sort of in this warm sort of surroundings right here. Now, what does this mean when it's in equilibrium? Well, it means that the temperature of this is exactly the same as the temperature of this. But you might be asking, well, what if the temperature changes? And this is where it kind of gets a little bit weird, because we actually say that we use an infinite number of heat baths. That's what a proper sort of, statistical physicist would say, is that you use an infinite number of heat baths. But in practice, a process is generally quasi-static if it's done slowly enough. If you increase the volume or increase the pressure slowly enough, then it will always be in equilibrium with its surroundings. So I know that's a very unusual concept, and I can appreciate that it's not a very good way to get around the problem, but it does tend to work. The maths still holds. Experimentally, the maths tends to work. And so this is true for a quasi-static process, but in reality, the process will not always be quasi-static. The quasi-static is kind of like the best you can get kind of thing, but we'll go into that a little bit more when we're talking about the second law of thermodynamics. I just want to go over what adiabatic processes of ideal gases are for the moment. So here's our definition of entropy. ds equals dq divided by t right here. And really what I should put is a little thing here to remind us that it is quasi-static. The process is quasi-static. So that's entropy. We'll park that formula for now. We're going to use it a little bit later on. But now I just want to go and derive a relation for an adiabatic process. So let's start with the first law of thermodynamics. Delta U equals Q plus W. I said that Q is 0 for an adiabatic process. So therefore delta U is simply the work. So the change in internal energy is simply the work being done. So let's go ahead and take the differential form of this, like we did in the last video. So du, which is a tiny infinitesimal change in internal energy, is equal to dw. But what is dw? Well, dw is just the same as minus p dv. That relation we used a lot in the last video, quite a fair bit. So we get that du equals minus p dv. But how do we evaluate du? Well, we need to use our good old approximation of the ideal gas yet again, and that u is 3/2 pv, which is true for an ideal gas, this is. And what is du? Well, again, using the product rule, which is what we did in the last video, we simply said it was 3/2 into p dv plus v dp. Now remember, this process is adiabatic, so I've said nothing about volume being constant or pressure being constant. So unfortunately, we can't really delete any of these terms as much as we want to, really. So we've got du equals 3/2 p dv plus v dp, and now we can substitute this back into this equation here. So we get 3/2 p dv plus v dp is simply equal to minus p dv. And if we rearrange this formula, we get that 5/2 p dv is equal to minus 3/2 v dp. So what can we do with this? Well, we can actually do a kind of a well-known way of solving differential equations, which is called separation of variables at this point. We've got something in terms of v, and we've got something in terms of p. Now what we can do is we can divide both sides by pv. And so what are we going to end up with? Well, we've got the 5/2 on this side. Divided both sides by pv, we're going to get a 1/v on this side dV, and that's equal to minus 3 over 2 1 over P dP. Now, before I go any further, you can immediately see that the 2's are going to cancel out, so let's just rub these out, we might as well. So we've got a 5 on this side and a 3 on this side, and now we can integrate both sides. So this is the technique that we're using, it's the separation of variables. So what happens when we integrate this? Well, let's put a little integral sign, and let's also choose some limits. So let's just say that we're going between the initial volume and a final volume, and let's just say we're going here between the initial pressure, not VI, PI, an initial pressure to a final pressure. So we're just adding some arbitrary limits here. We don't know what any of these are, we're just adding arbitrary limits at this point. Integral of 1 over V, well, we're going to get let's just write that 5 underneath, we're going to get 5 multiplied by the log of V evaluated from VI to VF is equal to minus 3 times the log of P evaluated between PI and PF. And what we can do is we can divide both sides by 3 and get that 5, or minus 3, let's go, minus 3, so minus 5/3 ln of V evaluated between these limits is going to be simply VF divided by VI. The reason that is because of the logarithm law. If you've got log A minus log B, it's going to be log of A divided by B. That's quite a well-known log law, and I did show it in the last video, so I'm just going to skip that step, and that is equal to the log of PF over PI. So another log law that you should be familiar with is that you can simply bring this minus 5/3 up to the exponent right here. That's how logs work. And also, you should know that if you have this minus 5/3 up here, you can change it to plus 5/3 if you switch these two variables around. So let's go ahead and do that all in one go. So we're going to get log of VI divided by VF is equal to the power of 5/3 is equal to the log of PF divided by PI. And so now we just got log of something equals log of something. So let's just get rid of those logs. We don't have to worry about them anymore. So we're going to get VI over VF to the power of 5/3 is equal to PF over PI. And you can multiply out these fractions just to get rid of all these fractions. So you can get PI on this, which is going to come on this side of the equation, multiplied by VI to the 5/3 is equal to PF times VF to the 5/3. And so what have we got here? Let's just have a little look at this. PI VI to the 5/3 equals PF VF to the 5/3. In other words, PV to the 5/3 is a constant. It doesn't matter what pressure and volume you have, PV to the 5/3 is a constant. And that is the adiabatic condition. This is the quasistatic adiabatic condition, and it's quite useful if you want to calculate sort of what the final volume is or the final pressure is. Use this relation and you'll get PV to the 5/3 is a constant. Now similarly, you can derive quite a similar relation. Instead of pressure and volume, you can use temperature and volume. Just remember, what is the ideal gas law? Let's just go over here. PV equals nRT. And so let's just substitute what P is. So P equals nRT over V. And let's substitute that into this expression here. We're going to get that nRT over V multiplied by V to the 5/3 is that constant. But what's going to happen here? Well, this v to the 5/3 is going to kind of cancel with this v here, but it's going to cancel to give v to the power of 2/3 multiplied by nr t, which is a constant. And what I've been doing throughout this entire video is setting n to be constant. The number of moles is constant, and so since n is a constant and r is a constant, then we can just simply define another constant in the same way. So tv to the 2/3, remember we're dropping the nr, is just another constant. It doesn't matter what it is, it's just the constant slightly different. But this is also true for an adiabatic process. So we've derived that pv to the 5/3 is a constant and tv to the 2/3 is a constant. You might, instead of seeing 5/3, you might actually see the symbol gamma. Gamma is often used. And why have we called this thing gamma? Well, what was 5/3? We kind of seen this 5/3 somewhere before. Well, 5/3 is simply the ratio between CP and CV. Remember, CP was 5/2 multiplied by R, and CV was 3/2 multiplied by R. And when we took the ratio, well, you're going to get 5 divided by 3 is just, 5/3. And so we define this to be gamma, and that's only true for a monatomic ideal gas. If you had a diatomic ideal gas, you'll actually get 7 divided by 5, 7/5 as gamma. So I'll just write this out. So gamma for a monatomic is 5/3. Gamma for a diatomic is 7/5. And the reason for that is you have 2 extra degrees of freedom for a diatomic gas, which therefore ups all the values by 2. So 5 becomes 7 and 3 becomes 5. But more generally, you say that PV to the gamma is a constant, where gamma in this case is 5/3, or likewise TV to the gamma minus 1 is a constant. So, but generally you'll be dealing with monatomic ideal gases, so I thought I'd just sort of show, that gamma is mostly going to be 5/3. If you're in like a situation, gamma is probably going to be 5/3. So we're now going to move on to the second law of thermodynamics. And we briefly touched upon it earlier when we were talking about entropy, because second law is all about entropy. Remember, I defined entropy, the change in entropy, as being the heat, delta Q, divided by T, right here. So delta S equals delta Q over T. But then I also said that this is only true in a quasistatic process. So therefore, this relation only applies in a quasistatic process. More generally, the change in entropy will actually be is going to actually be greater than delta Q over T. And this is a very important thing in thermodynamics, is that entropy can never be negative. You can never have a situation where delta S is less than delta Q over T. It's always positive. And so what I can actually write is that delta S is equal to delta Q over T plus some extra delta S, some extra entropy. And this is irreversible. This term right here is irreversible entropy change. Once it's done, you can't go back. It's irreversible entropy production, and it's always positive. This term is always positive. You can, in fact, have a situation where this term is negative. This term, the delta S in total, will always be positive. That will always be more positive than that is negative, if it happens to be negative. You can definitely get from a higher entropy to a lower entropy, but not irreversibly. The best you can get is a quasistatic process where you have delta Q over T. So the way that this is summarized is in the form of the Clausius inequality. And the Clausius inequality says that delta S is greater than or equal to delta Q divided by T. So it can be equal to it, but it's always going to be greater than, because you'll have this irreversible entropy production. And that results if the process is not being done quasi-statically. So this is the quasi-static case. This is the general case. That should really be a greater than or equal to sign. This is also the general case right here. You've got this extra term, the irreversible entropy production, and this is the Clausius inequality. And so this is going to be quite useful. Now, you can actually take the differential of this second law of thermodynamics and say that ds, which is an infinitesimal entropy change, is equal to dq divided by t. And for the moment, we're going to focus on the quasi-static case. And if you want to get the total entropy change, then you simply have to do an integral over all entropies over ds, which is exactly the same as the integral of dq divided by t. Remember, this is all quasi-static. We're just going to pretend everything's all quasi-static from now on, so we don't have to worry about extra terms like this here. So that is how to calculate the change of entropy, and this is what we're going to do. We're going to now calculate what the entropy is of an ideal gas, it's quite a complicated thing to do, but this will form quite a good basis for some of the things that we're going to be doing in statistical physics. So we're going to calculate the entropy of an ideal gas. An entropy of an ideal gas. So let's go ahead and say that, so delta S, let's just rewrite this relation out. This is our first step, if you like, is the integral of dq divided by t. But we showed earlier from the first law of thermodynamics that dq equals du minus dw. So this is what we're going to get for dq. Dq is a hard integral to do because typically dq will depend on various things like temperature changes and volume changes, so it's hard to integrate over one thing. But we're going to split this apart and use it for several different integrals. So what did I say du was? Well, I used this relation before. It's 3 over 2 into p dv plus v dp, our good old friend the product rule, minus dw. Well, dw is minus p dv, so we can simply add another p dv onto that. So we're going to yet again get 5 over 2 p dv plus 3 over 2 v dp. And remember, when I was doing the adiabatic derivation, this was just all equal to 0, because of course dq is equal to 0. But now we've got a more general thing. Remember, this is not for any type of process. It's not isothermal, it's not isobaric, it's not adiabatic. It's generally what is the entropy of an ideal gas. And so dq equals 5 halves p dv plus 3 halves v dp. So let's go ahead and substitute that into our equation for entropy. So as you can see, we've got two of these infinitesimal terms, so we're actually going to get two integrals. So let's start by adding the first term. So we're going to get 5 over 2 p dv, but divided by the temperature right here. So 5 over 2 p over t dv. That's our first term, but we're also going to get another term. We're going to get 3 over 2 v dp. That's delta Q right here, divided by T. So this is our current expression for the change in entropy. And now we've got to use, you guessed it, the ideal gas law again. So what's P over T? Well, let's start with PV equals nRT. So what's P divided by T? Well, P over T is nR divided by V. And remember, we're treating n as constant again. We're not going to vary n for quite a little while now, but soon we will, and we'll do the more general case, but we're going to keep n constant. And what's v over t? Well, v over t, probably almost exactly the same in way as p over t. V divided by t is nr over p. So we're going to use these two relationships and substitute them into our formula for the change in entropy. So delta S is equal to 5 over 2 is a constant, we can bring that out the front. The integral of nr over v, dv, plus 3 over 2 integral of nr over p dp, right here. So it's starting to get a little bit long, this, isn't it? And now we can integrate these terms. So we're going to get, well, nr is just going to appear on both these terms. So we might as well just factor out this nr. And we've also got this 2 hanging around the front, so we might as well just get rid of that, and so put nr over 2 right at the front. So these terms have all moved out, and so is the 2 from both of these. So we're going to get 5 multiplied by integral of 1 over v is the log of v. And of course, really, I should have put in limits right here. So we're going to get vi to vf again and pi to pf again. But actually, there's almost exactly the same thing will happen as before. So we're going to get the log of vf over vi plus 3 times the log of pf over pi. Okay, so now what I'm going to do is I'm now going to try and divide everything in this bracket here by 3. And if I do that, then I'm going to have to multiply this term by 3. So I'm going to get 3 over 2 nr. So that's been multiplied by 3. So everything in this bracket here now is to be divided by 3. So we're going to get 5/3 ln vf over vi plus ln pf over pi. And now what I'm going to do is I'm going to use the law of logarithms to write that 5/3 ln vf over vi. The 5/3 simply comes up to the exponent, and so I'm going to get log of vf over vi to the power of 5/3 plus the log of pf over pi. And now we can use the additive rule of logarithms to show that this is going to now go to a single log. And what happens when we use the additive rule? Well, we multiply these terms together. So we're going to get log of pf vf to the 5/3 divided by pi vi to the 5/3. And this is kind of almost exactly the same as what we derived before. So this is the change in entropy. And what I can actually write, you might find this step a little bit weird, is that just the total entropy is exactly the same as this. So 3/2 nr times the log of, you see, I said that pv to the 5/3 is essentially a constant, just like in the adiabatic process. You can use that pv to the 5/3, so just any general p and any general v, all raised to the 5/3, divided by a constant. Now, this constant is constant for p, v, and t, but it does in fact depend on n. So I won't write that it's a complete constant. I'll just simply write that it's a constant that depends on n. And so this constant, we will actually find out what this constant is a little bit later on. But for now, this is our best looking form for the entropy of an ideal gas. We'll have a bit more information when we work out what this constant actually is. So there we go. That is the entropy of an ideal gas. And finally, to round it off, the third law of thermodynamics. The third law is quite a simple law, so there's not really that much maths about it. The third law states that the entropy approaches 0 as the temperature approaches 0. So as T approaches 0, the entropy must approach zero. That is the third law of thermodynamics. Or more generally, you say it actually approaches a constant, but most of the time is zero. So that is just the third law of thermodynamics in a nutshell. It's not very complicated. And so, yeah, I'll see you guys in the next video, in which we're going to be talking about thermodynamic potentials.